In this talk, I'm going to introduce our recent paper, Low-Rank Matrix Rigidity, Tight Lower Bounds, and Hardness Amplification. This is a joint work with Josh. Let me start the talk by introducing the central concept of this talk, matrix rigidity. The concept of rigidity was first proposed in the 1970s in the context of understanding circuit complexity. Given a matrix A over a field F, the rigidity of A with respect to rank R is the minimum number of entries we need to change in A to reduce its rank to at most R. Equivalently, it asks, what's the best way to write A as a sum of a low-rank matrix L and a sparse matrix S, where the rank of L is at most R, and we want S to be as sparse as possible. We say a matrix is rigid if, no matter how we try, S has to be dense, meaning that A is far away in Hamming distance from any other low-rank matrix. This concept of rigidity is important in the sense that proving rigidity lower bounds translates to hardness results in many computational models. There are a number of known reductions, saying if we can prove strong enough rigidity for an explicit matrix at the right rank, it implies lower bounds in circuit complexity, communication, and more. There's a technical point. In our work, we focus on rigidity over either finite fields or the complex numbers, two settings where such reductions are well understood. As a quick overview, this work proves new lower bounds on matrix rigidity in low-rank regime and reveals a surprising connection between different rank regimes. I will describe these results more precisely in a few minutes. So let me first talk about the rank regime we care most. In fact, actually, for most of rank regimes, we still don't know strong enough rigid lower bounds to obtain meaningful applications. So suppose our matrix A is n by n. Let's begin with the high rank regime, which is originally started by Valiant in 1977. Valiant asked, can we reduce the rank of A by a factor of log n by changing just n to the 1 plus epsilon entries? And he showed that this type of rigidity is related to the circuit complexity of computing a linear transformation that maps a vector x to A times x. In particular, if one can prove a matrix A is Valiant rigid, then using variance reduction, one can show that the corresponding linear transformation cannot be computed by any depth or log n linear circuit with size On, which matches the many classical upper bounds like those using the fast Fourier transformation. Despite this importance, we currently don't know how to prove Valiant rigidity for any explicit matrix. In fact, some matrices once conjectured to be Valiant rigid have been shown not to be rigid in the last decade. Let's now move to the mid-rank regime, which was first explored by Razvarov. In this setting, we aim to reduce the rank of A to something like quasi-polylog n. which is larger than any polylog, but still far smaller than any polynomial. And now we are allowed to change a constant fraction of all the n squared entries. Razborov showed that such rigidity of a matrix A is closely related to the complexity of the following communication problem, where Alice and Bob have indices x and y respectively, and they want to communicate and coordinate to compute the xyth entry of a matrix A. And if one can prove a matrix A is Razborov rigid, then we can get a super strong communication lower bound using Razborov's reduction. The communication lower bound will be even beyond polynomial hierarchy. More recently, people have started studying the low rank regime, where the target rank is just polylog n. This form of rigidity is connected to the power of constant depth circuits computing the linear transformation defined by A. For example, Alman in 2021 used low-rank rigidity upper bound to build a depth 2 linear circuit of size n to the 1.476 for the Wash-Adama transformation. In this regime, we usually allow up to n squared times half minus log of 1 entries to be changed. This is very generous when considering rigid upper bound. As for binary matrices that we care most, there is a trivial way to change at most half of the entry to make it rank 1, just by changing all the entries to be the same. We are just to be happy as long as we can do slightly better than this trivial algorithm. So, in other words, proving a rigid lower bounds against this low-rank regime with such a n squared half minus log of 1 sparsity would be challenging, and this will be the main focus of this work. Before stating our results, let me clarify the class of matrices we will consider. First, we focus on explicit matrices, those that can be constructed by a uniform deterministic polynomial time algorithm. Say, if we remove this restriction, then a simple counting argument can show that random -1, 1 matrices are highly rigid with high probability. But that doesn't help us prove uniform lower bounds in other models, since random functions in other models are also automatically very hard. And in this talk, we focus on a canonical family, the Wash-Adama matrices. The nth Wash-Adama matrix Hn is a 2 to the n times 2 to the n matrix, defined recursively by 4 copies of Hn-1, where the bottom right copy is negated. This family plays an important role. The corresponding linear transformation is useful in practice, and the corresponding communication problem is simply computing inner product mod 2. For simplicity, I will state our results in terms of Wash-Adama matrices, although they generalize to other matrices family defined by chronic product or majority product. You can find them in our paper if you are interested in that. So what do we know about rigidity of Wash-Adama matrix? Unfortunately, as I mentioned, all the rigidity lower bound that we know are not strong enough to imply hardness in the computational models that we discussed. Among all the known rigid lower bounds, a large fraction of them are based on so-called untouched submatrix argument. This argument is based on a simple observation that in order to reduce a matrix, the rank of a matrix below R, we need to change at least one entry in any rank R submatrix of A, since the rank of A is lower bounded by the rank of any submatrix of it. In the ideal case where all the R by R submatrices of A are 4 rank, then every R by R submatrix must to be touched, and we can lower bound the rigidity by solving a combinatorial optimization problem. That is, how many entries do we need to touch to cover all such R by R submatrices? By solving this, we get the rigidity lower bound of n squared over R times log n over R on such ideal matrices. And for Walsh-Adama matrix, it is a little bit worse, as not all the R by R submatrices of it are 4 rank. But we can still use this type of argument to prove a lower bound of n squared over 4R, which is also the state-of-the-art rigidity lower bound for Walsh-Adama matrix. Comparing to the requirements of the previous reductions, this lower bound is still far away by a factor of at least quasi-polylog to obtain valiant or Rathbone rigidity. Say, for valiant rigidity, we only obtain a sparsity of n times log n, and for Rathbone rigidity, we only obtain a sparsity lower bound of n squared over quasi-polylog n. Besides untouched submatrix argument, there are also some other works that prove lower bounds against a variant of rigidity called bounded rigidity. In the bounded rigidity, in addition to sparsity, each entry of the error matrix S should be bounded in magnitude by some parameter theta. This bounded version of rigidity is much easier to deal with than the regular one. There is very strong rigidity lower bounds against this type of rigidity where the sparsity is nearly optimal. However, such lower bounds heavily rely on the boundness assumption, hence cannot generalize to the standard rigidity and only work on the number field C instead of finite fields. Okay, with all these backgrounds, let me now set our main results. Our first main theorem is a tight rigidity lower bound of rank up to O log n, showing that for any constant prime p, the rigidity of Walsh-Adama matrix over finite field Fp with respect to rank log n is at least n squared times half minus n to the negative O1. This lower bound matches the sparsity known for bounded rigidity, but crucially, it applies to the standard rigidity over finite fields. It improves the previous state-of-the-art rigidity lower bounds for any explicit matrix in the low-rank regime. The previous state-of-the-art rigidity lower bound for rank log n is only omega n squared, and we improved the hidden constant in omega into the optimal 1 over 2. Our second result is a hardness amplification result, showing that if one can further improve our rigidity lower bound to a slightly larger rank, log to the 1 plus epsilon n, even with a slightly worse sparsity, then it will imply Rutherford rigidity of Walsh-Alman matrices. This result points out a new way to think about Rutherford rigidity. Instead of considering a larger rank of quasi-polylog, in order to prove Rutherford rigidity, it suffices to fully understand the rigidity for rank near log n, which seems much closer to what we've already known. There's a technical point I should mention. Actually, our second result is about a slight variant of rigidity. We omit the distinction here, but the details can be found in our paper. So finally, let me briefly outline our main idea for proving these two theorems. The main idea of proving our rigidity lower bound is reducing it to bounded rigidity over complex field. Specifically, we establish a transformation that allows us to take the low-rank approximation L of Hn over finite field as an input and transform it to a binary matrix L tilde, which approximates Hn as well as L, with its rank bounded over complex field C and suffering an exponential blow-up in the rank. This reduction allows us to port bounded rigidity lower bounds to the standard setting, achieving bounds that match the bounded case, something not known before over finite fields. Our second result relies on a self-reduction. Suppose we have a rigidity lower upper bound for a smaller Walsh-Alman matrix HK. Then we can use it to construct a low-rank approximation for a larger matrix Hn, where the rank should keep small, but we are allowed to change close to half of the entries. Our theorem 2 follows directly by plugging Rutherford rigidity into the self-reduction. The idea of proving such a self-reduction is quite natural. To construct a low-rank approximation of a larger matrix Hn, we will approximate it in two steps. So in the first step, we will write Hn in terms of Hk, and then replace each appearance of Hk by Lk, which greatly reduces the rank. Then, in the second step, we will apply some polynomial method between these copies of Lk's to further reduce the rank below the desired threshold. However, it's a little bit tricky to analyze the error. One might try to bound the error in both steps separately and combine them by simply applying union bound. But that doesn't work because error in both of the two steps are very large. Each changes close to half of the entries. Fortunately, we can complete proof by observing a cancellation effect between two types of errors. Say, if an entry is changed in both steps, it may end up correct in the final matrix. By carefully analyzing the low-rank matrix under this cancellation effect, we can prove the self-reduction. And that concludes my talk. Thanks very much for listening.